umbilical, and then the cabinet itself. Next slide. I won't get into a lot of details. I just want to point out a couple of features of the device as kind of a follow-up to our design criteria we set up. We're using an ejector pump to pull the sample through. So that means we don't have any diaphragm pumps or anything to maintain. We simply use instrument air to pull a sample down the sample gas line and through the system. And from the sample gas line, we're injecting the gas straight into a high temperature cell. And in the cell, this is where we're doing our conversion. I mentioned we were going to go to a high temperature conversion concept. And so we've got a cell that we heat to about 1,000 degrees C, and we're doing the conversion to elemental mercury and measurement in the same location. So we can eliminate any worry about possible recombination in the sample system. And then below that, of course, we've got the optical unit with our light source and detector, and then the external calibration unit and all the necessary electronics that are required for a standard SEMS. Next slide. Here you can see a picture of what the internal cell looks like, heated. It's a double-walled cell, so we bring the gas on the outside wall, do the conversion, and then we put it into the internal area of the cell where the measurement takes place. Next slide. And here's what it looks like in practice. The oven surrounding it is actually as much for protection as anything, where it's much hotter in the middle, cooler in the outside, so we can get the temperatures in a safe way without compromising safety. And the measurement principle is also a little bit unique compared to other mercury monitors. We're utilizing an effect called the Zeeman effect, where we've got a mercury light source around which we supply a magnetic field. And what the magnetic field then allows us to do is to split the initial light wave into two separate beams of opposite polarizations. And by putting them through some optics, this photoelastic modulator and polarizer, we're able to generate alternating reference and measurement signals on a time scale of about 2 microseconds. So what I'm saying is that we have one light source with no moving parts, just some simple optics, and we're able to generate a reference curve that shows a consistent reference point and a measurement curve on a time scale of about 2 microseconds. Next slide. What the advantage of this is, in fact, of course, it's a very continuous measurement. It gives very quick response. More importantly, relative to even our old mercury analyzer, it's no moving parts, very low maintenance over long periods of time, and very stable. The fact that we're using a single light source through a common set of optics also means that any contamination of the optical surfaces or any degradation of the light source affects both the reference and measurement equally, and it allows us to give a quick correction for that optically. Next slide. So I'm not going to read through all of these. I can certainly give people more information if they're interested later. But from our point of view, the most important thing to notice on here, and of course the accuracy is, as we discussed before, are all similar to other devices, but the maintenance interval we've seen in the field has been greater than 12 weeks. And there's a lot to be said about accuracy, and it's very important, especially in these kind of applications, but also something that's reliable and is not going to eat up a lot of maintenance budget. And so that was really the crux of the redesign. And just to give you a quick kind of introduction on the new technology here. I can move on now. The two other measurement requirements, flow I mentioned as a secondary requirement for PM SEMS and mercury. We would generally recommend the ultrasonic flow technology for monitoring of the flow. There's various different types depending on the application, depending on the duct size, the dust concentration. If you didn't have access to both sides of a stack or were trying to replace something like a pitot tube, you could go with a probe style ultrasonic to accomplish that. Next slide. There you go. Of course, the key to any ultrasonic device is the transducer. You want something that's very highly durable and low maintenance. All of the transducers that we manufacture and recommend are titanium-based or titanium-closed transducers as standard, and we offer a 3-year warranty on those transducers. So, you know, being as they're the heart of the system, you get maintenance intervals that are quite long with something that's warranted for 3 years. Next slide. The other thing that's really important to avoid when you're measuring with ultrasonics is if you can avoid the use of external purge air, it's very beneficial to the accuracy and overall operation of the system. There's really 2 main points to consider concerning this purge air. One is if you're blowing cold air from the outside across the hot face of a transducer, you can certainly see where you could start forming condensation and the possibility of acids forming and contamination of the transducer. The other thing that happens is you create unstable thermal conditions across the face of the transducer, which create noise and lead to inaccuracies and those kind of things. So eliminating that external purge is really beneficial from a maintenance and an accuracy standpoint, and we can supply these with no purge air up to process temperatures about 500 degrees F. Next slide. Total hydrocarbon. Typically, the most commonly used technique, of course, is the flame ion. I won't go through the whole theory of operation of an FID. It's quite widely used and meets all the performance specifications of the PC MACT. In the past, and I'm sure anyone who's got experience with THC analyzers will say that the biggest issue with them has not been accuracy, but the fact that they tend to require a lot of maintenance. You'll tend to see a lot of small capillary tubes and airflow things in a total hydrocarbon analyzer that create maintenance problems, plugging problems, and so we recently, as part of the process where we redesigned the mercury analyzer, we took a look at our FID and said, could we do this a better way? And we came up with this, what we call our FEDOR. It's again a hot wet extractive analyzer, so as we discussed earlier, it's possible to integrate that into an existing sample system. But the key to this in terms of a maintenance perspective is the fact that it's very modular. If you've got a solenoid bay where you've got an airflow block that's one block instead of a bunch of capillaries and fittings. So if you had an issue with plugging, you could simply replace that block and be back up and running in a short period of time. So, you know, the message here is really accuracy and long-term stability and reliability, because you know, if accuracy, there's always a trade-off between how much it costs to maintain something and what kind of accuracy you're getting out of it. And so if you can get something that'll give you both, that's always the beneficial, I think. Next slide. Just a quick summary. I want to hit on the fact that you know, experience counts, especially in the cement industry. There's a lot of specifics in terms of how the cement process operates, and you know, we've got a lot of experience in that, and even if it was integration of other devices, you know, we would do that as far as driving towards what we call best solution, and we make that solution application driven, not technology driven. So I think the next slide is the end. So I appreciate the time again, Bob, and I'll certainly be happy to answer any questions.
Yeah, let's get people asking questions, but while I'm changing over here, a lot of these cement plants are relatively small and will not have, you know, adequate staff. Mm-hmm. So they're going to be, one way or another, having to integrate with people like yourselves or service providers and so forth.
Yep.
What is your recommended solution when you run across a plant, you know, that is relatively small and needs a lot of help?
Yeah, I think in general, you know, and Carl talked about this, the performance of a CEM is only going to be as good as the maintenance because there's certainly no such thing as a maintenance-free SEMS. You know, our standard solution or our standard offering to customers would be two things. All of our devices offer some sort of remote diagnostic capability where we can either remotely access it through the existing plant network or wirelessly over a cellular GPS signal. So that would be one leg of the solution. But I think more importantly, getting continuous training and perhaps even investing in a maintenance contract for at least some period of time. Because of course, this being a new monitoring requirement for this industry, there's going to be a learning curve on the analyzers and the technology. And so getting somebody that would come in on a regular basis to help you work through routine maintenance, learning on the job, really, I think, helps close that gap in a short period of time.
Thanks for that answer. And other questions from the floor? You mentioned a particulate SEMS that the EPA allowed, and you use a number of 25% variation. I guess I would go back to the question that I think I posed earlier to Carly, that you've got one requirement for what EPA says is the minimum reliability, but you have another one that impacts your total, PM requirements per ton of clinker and so forth, and therefore the less reliable the monitor, the more higher efficiency the control equipment is going to have to maintain in order to give you a safety factor. Is that not correct?
Yeah, you're right. I mean, I think the PS11 was written in broad brush terms, and I would say from our experience, and I'm sure this has been the experience of a number of vendors, the response of the analyzers have been much better than the range we were given by the PS11. For instance, the correlation coefficient that's defined by PS11 that the initial correlation audit has to meet, there's requirements in the PS11 that says it has to be greater than 0.85 when you do the correlation between all the points. Most of our experience has been that the PM SEMS will be better than 0.98. So, in terms of performance, we've seen much better performance than the rules actually required it to meet. So, certainly something to consider when you're looking for vendors is what kind of performance have you seen against PS11? Because as you point out, there's just because you can meet PS11 doesn't mean you're getting all these other benefits that the accuracy of a device can give you long term.
Lots of challenges. Other questions from the floor? Well, we will be getting a general question and answer session and getting into some of these issues, and I hope you'll come up with some thoughts too as we get into that. I'd like to thank you, Dan, for very comprehensive coverage of a lot of different pieces of the pie, so to speak, here that are all required if you're going to be monitoring under the new Cement MACT.
Appreciate it. Thanks.